Okay, so on Tuesday, we did kind of the first part of this, which included kind of the periodic table basics and the electron configuration information. So what we're going to talk about today is the second part, which is about our first periodic trends, which have to do with the size of our atoms. So we're going to be talking about atomic and ionic radii. And we're going to be relating it back to that electron shielding and the nuclear charge that we kind of had at the end of class on Tuesday. And then actually the stuff for next week's already posted because I have it posted for 8A for tomorrow. So if you want to get, head start over the weekend, that stuff is already up there. But I'm going to just click here really quick. So for Tuesday and today, it was kind of all combined into one page. And so the first 3 videos on here were what we covered on Tuesday, Monday and Tuesday, and then the last 2 videos are on atomic and ionic radii, and that's what we're going to talk about in a little more detail today. And then after today, you should be able to complete that first note check with the exercises that are over these sections. Okay, and so if I go to the next page, it has where you can submit your note check after today. And so basically, pages 4 through 8 is where you should be annotating, taking notes, adding in information, highlighting, drawing things in, color coding, whatever. And then at the bottom of page 5, there are a few exercises, not a lot. And then all of page 9 has exercises and questions that are going to relate to what we're talking about today with atomic and ionic radii. Okay. So I'm going to switch over to the iPad so we can do some notes. So I just really quick, last time we did that first part, so I'm going to go back up here to this checklist just so we can kind of see it as we're going along. So what we did on Monday and Tuesday, we covered this first one, we covered this second one, we covered this third one, and then at the very end, we started talking about this fourth one. So we're going to go back and kind of recap that one today. And then today, after we kind of recap that, we're going to cover this one, the trends for atomic radius, the trends for ionic radius, down a group and across a period. And then next week is when we'll be getting into the next things about like ionization energy, electronegativity, and electron affinity. So all the information that's here on this chart on page 2, we'll be done with that after next class. And then the rest of it we'll be doing later next week and after that. Okay. So last time we did kind of a quick recap of the basics of the periodic table. What's a period? What's a group? What are the different families or the different groups that you need to be aware of so you can color code them on your periodic table. So things like alkali metals, halogens, and all the other ones that are here on this list that you have on page 4, I believe. Yeah, page 4. We talked about how the electron configurations fit in on the periodic table. So they're arranged in a way that the sublevels are all in specific areas. And so you should, if you're given an electron configuration, you should be able to identify where an element's located. So what period, what group, and then what block it's in. So is it the S block, which is where you would find the S sublevel, the P block, which is where you would find the P sublevel, etc. Or if I'm given an element, I should be able to write or predict its configuration just by looking at where it's located on the periodic table. Okay. And then the last thing we talked about was this electron shielding. And so we talked about the fact that shielding, it means that you're blocking something. So when we're talking about atoms and electrons inside of atoms, what we're talking about is that any electrons that are on the inside or the inner energy levels, those are called shielding electrons, as it says right here. And so on this image down here, all of these here, so the first, the second, and the third energy level that are highlighted in yellow, those all contain shielding electrons because they are inner energy levels. Out here, the very last one that actually contains electrons on this picture is the fourth energy level, because here's the valence electron right here. So this element is actually, I believe it's potassium. Yeah, it's potassium because it has 4 energy levels and it has 1 valence electron in its 4th energy level, which would mean that it would be the element potassium. And so what the concept of shielding means is it just means that this valence electron, or any valence electrons that are in your outermost shell, they are shielded or blocked from feeling the full attraction of the nucleus, because all of these other electrons on the inner energy levels are kind of acting like a barrier. So they're affecting how much the nucleus can pull. So here in the center, the nucleus has all the positive charge because that's where all the protons are. And so if I'm talking about maybe this electron right here on the first energy level, that's feeling the full attraction because it's right close to the nucleus. There's nothing in between those electrons on the first energy level and the nucleus. But then as I go out to the second energy level, now it's going to be shielded from those electrons on the first energy level. As I go to the third energy level, those are going to be shielded by both the first and the second energy levels. And then our valence electron out here which is on the fourth energy level on this Bohr model, is shielded by all 3 of the levels that are in front or in between it and the nucleus. So the reason that's important is because shielding affects what we call the nuclear charge or effective nuclear charge. And the effective nuclear charge is basically what causes atoms to have different sizes. Okay, it's one of the key things. Having more energy levels obviously affects the size. More or less energy levels, they're going to be larger or smaller. But also the nuclear charge, because that is talking about the attraction of the protons in the nucleus to your electrons that are in these different energy levels. And so we talked about that as you go across left to right, shielding is constant because as I go across a period, I'm not adding any energy levels. I'm just adding more valence electrons on the outermost shell. And so because I'm not adding any energy levels, the shielding is the same across the row because there's no more inner electrons being added. The electrons are all being added to the outermost valence shell. Down a group, though, it does change. As I go down a group, the shielding increases. And that's because going down a group, I am increasing the number of energy levels because every time I go down to a new period, I have one more energy level. And if I have more energy levels, that means there's increased shielding because there's going to be more electrons on those inner levels that are going to be blocking the valence electron from feeling the full attraction of the nucleus. So how does that affect the nuclear charge and then the size of our atoms that we're going to talk about today? Well, we have sort of 2 terms here, nuclear charge and effective nuclear charge. So nuclear charge is like the total charge of the nucleus. So nuclear charge is the same thing as the atomic number. So, if I have, let's say sodium on the periodic table is atomic number 11. So sodium's nuclear charge would be 11 because it has 11 protons in the nucleus. Okay. And as I go kind of across my periods on the periodic table and I work my way down, my nuclear charge increases by 1 because that's how my atomic number works. Okay. Because every time I move to a new element, I'm adding 1 proton to the nucleus, and therefore the nuclear charge is increasing by 1 every time I move to a new element on the table. Okay. What happens is, though, the outer electrons, which are our valence electrons, they don't experience the full attraction from the nucleus because of that shielding, okay, like we just talked about. And so we have this other term for what the valence electrons feel, what charge they feel. And so we call it the effective nuclear charge because it's what's actually affecting the valence electrons. Okay. And so it says here that it's the net positive charge experienced by the valence electrons. And whenever you see here a net of something, that means basically you're going to subtract. Like if you own a business and you need to report like your net profits, for tax purposes, your net profits are like how much total profit do you earn minus all your expenses. Like if you have employees, you have to pay their salaries. If you have equipment and materials you have to buy, you have to pay for that. If you have to pay rent for your building, you have to pay that. So net means that you're subtracting like a total minus something. So in this sense, we're subtracting the total number of electrons, which is going to come from our atomic number because we're going to assuming that our atoms are all neutral. And so effective nuclear charge, it's less than the actual nuclear charge. And here's the little equation. I do the atomic number, which is going to be the total number of electrons in my atom, since electrons and protons are going to be the same as long as it's a neutral atom. And I subtract the number of shielding electrons, because those are all the ones on the inner energy levels. And so when I subtract, the difference that I'm going to be left with is called the effective nuclear charge. And that effective nuclear charge is going to be equal to the number of valence electrons. Okay, so for example, if I were to, I'm going to draw a Bohr model here. So I'm going to draw sodium. So sodium is an alkali metal. It is in the third period. So it's in group 1, period 3. 4, 5, 6, 7, 8. Okay, so the first energy level is full. It's got 2 valence electrons, or not valence, 2 electrons. The second energy level would be full, and so it would have 8. And I'm sorry, my dots are a little messy, but I don't have the best pen to work with here. And then it's on the third period, so I would have the third energy level, and it's in group 1, which tells me that it has 1 valence electron on that third energy level. So this is what the Bohr model for sodium would look like. And so since there are 11 total electrons, the atomic number, or the total number of electrons, would be 11. And then I need to subtract the shielding electrons. And so remember, the shielding electrons are going to be the ones that are on the inner energy levels. So on sodium, the shielding electrons are going to be 10, because there's 2 on the first energy level and 8 on the second. And so when I subtract 11 minus 10, I get 1. And so that's the effective nuclear charge. And it kind of corresponds to the fact that sodium has 1 valence electron. And so that is what we would identify as the effective nuclear charge. So why is this important? Well, it's important because depending on that effective nuclear charge and how attracted the electrons, and specifically the valence electrons, are, that directly affects the sizes of our atoms, and that it also directly affects some of the trends that we're going to start talking about next class, in terms of how much energy does it take for me to remove a valence electron, or how easy can an atom attract an electron from another atom. So there are all these different properties that we're going to talk about, how they change going across a period or down a group, and pretty much all of them directly relate back to these concepts of shielding and nuclear charge, because that is what causes the atoms to have different sizes, and then that in turn affects the amount of energy that's needed to remove an electron, or some of the other ones. So today we're focusing on sizing of the atom. So first is going to be atomic radius. If you remember from your geometry classes, radius, typically we define it as, if I have a circle, the radius is the distance from the center to the edge of the circle, okay? So it's the same concept here, but the way they word the definition is slightly different, okay? So because they define it as, it's measured as half the distance between neighboring nuclei. So we can't just measure one single atom. And so what they do is they will take two atoms with 2 different nuclei. And if they were to put them next to each other, it's the distance between those nuclei divided by 2. And so here's kind of the distance. And then you can see if I were to like divide it in half, okay, right here, it is the same. It is the distance from like the center to the edge. But the actual definition, you have to define it as half the distance between neighboring nuclei, okay? If you are needing to look up values for atomic radii or ionic radii, either one, to help you answer open-ended questions, you can find them in the data booklet that you have access to on Canvas, and it's in section 9. So section 9 has a periodic table, and on that periodic table for every element, the atomic and ionic radii values are labeled on there, okay? So how does it trend? Because this is the important thing. We need to understand and be able to kind of explain how and why it changes, or how it trends going across a period left to right and going down a group from top to bottom, okay? And so on here, there's sort of a visual picture. And so we can kind of easily see that if I follow this arrow and I go left to right, the atomic radius is decreasing as I go across that period left to right. So here's sodium, which was that atomic number 11. As I go across the third period and all the way to chlorine, And we left off the noble gases, okay, but argon would be on here. It'd be a little smaller than the chlorine. But as I go across, you can see the atomic numbers increasing, right? So if the atomic number is increasing, that means the effective nuclear charge is increasing as well, okay? And so that is why they get smaller. They get smaller because the nuclear charge is increasing as we go across. And so if there's a higher nuclear charge, that means there's more attraction to all of the electron energy levels. And that means that they start to shrink, they pull in because there's more attraction. So this is the one that people typically have a hard time like sort of remembering or like wrapping their head around, because we tend to think that as I go across, oh, I'm adding protons and I'm adding electrons. So if I'm adding more of something, we automatically think, oh, it should get bigger. But that's not the case. And the reason for that is because all of the electrons are being added on the same valence shell. So I'm not increasing the energy levels as I go across. And all the protons are being added into the nucleus. And so that concentrated positive charge in the nucleus gets stronger as you go across, because the nuclear charge is increasing and it's pulling that valence shell in closer. And so that's why if I were to compare like sodium to chlorine, chlorine is going to be a lot smaller than sodium because it has a higher nuclear charge due to the fact that it has more protons in the nucleus, okay? And that's basically what the other little bullet points here say. It just says electrons are added to the same main energy level. So the shielding is constant. There's no increase in shielding. But since the electrons are all added to the same level, the protons pull them in when there are more protons to attract them. And that's what causes the atomic radius to decrease. And so if you were to look, for example, over here at these electron configurations for these elements that are in the third period, if I look at their valence shell, which is what I just kind of highlighted in green over here, it's written in red, or it's typed in red. Sodium, it has 1 valence electron. Magnesium has 2, aluminum has 3 valence electrons because it's got 2 in the 3s and 1 in the 3p. Silicon has 4, phosphorus has 5, sulfur has 6, chlorine has 7. And so remember, we talked about that effective nuclear charge is going to be directly correlate to the valence electrons. So that means that if this has 1 valence electron, its effective nuclear charge is going to be 1. And so as I go down, because the valence electrons are increasing, the nuclear charge, or the effective nuclear charge, is increasing as well. And so I can see that kind of with the electron configurations. I can see it with this actual size of the atoms, if I were to look at the actual sizes of them. Now, going down a group, okay, the atomic radius increases going down a group. And the reason for this one's a little easier to understand, because as I go down, if I go down a group, so this is showing us the elements, the alkali metals in group 1, so starting with lithium and then sodium, potassium, rubidium. So they all have the same number of valence electrons. Like if I look, they all end in something S1. But if you notice, the energy level that it's in is changing, okay? For lithium, it's the second energy level that valence electron's in. So it only has 2 energy levels. Sodium, if I go down, that's in the third period. So it has 3 energy levels where its valence electron is. If I go down to the next one, potassium's in the 4th period. So it's got 4 energy levels. And then rubidium would be in the 5th period. So it has 5 energy levels. So as I go down a group, because I'm adding more energy levels, that causes the electrons to be further away from the nucleus, and that results in a weaker attraction between the nucleus and those valence electrons. So kind of to summarize, going down a group, atomic radius increases due to an increasing number of energy levels. Going across a period, atomic radius decreases due to an increase in nuclear charge, okay? And so that's how you would kind of explain those 2 things. Now, the other thing we're going to talk about today, it's still dealing with size, but now it's not going to be neutral atoms. It's going to be ions, so either positive or negative charges. And so positive ions work one way, negative ions work a different way. And so that's what we really need to hone in on, and what we need to know is how do positive ions work and how do negative ions work, and sort of how they're different, okay? So for positive ions, remember positive ions are also called cations. And these are going to be our metals. Remember, metals are the ones that form cations because they are the ones that lose their valence electrons. So here we're looking at sodium. So this picture on the left is a sodium atom, which means it's neutral. That means that it has the same number of protons and electrons. Okay. So if I kind of look at, they've drawn the Bohr model, so I can see that if I look at the Bohr model, or if I look down here at the electron configuration, sodium has 2 valence electrons on the first energy level, has 8 on the second energy level because it's got the S and the P sublevels full. And then it ends with 3s1. So it has 1 valence electron and it's on the third energy level right here. Okay. And that corresponds to its location on the periodic table because it's in the third period, the third row, and it's in group 1. Okay. So third period means third energy level. Group 1 means 1 valence electron in that third energy level. So that's what the sodium atom looks like. And then here it tells us this is like the actual size. Like if we needed the actual numerical value, that's what the numerical value for the size of the neutral sodium atom would be. Now, since it's a metal, all metals lose whatever valence electrons they have when they become ions. And so sodium, since it has this 1 valence electron here, it's going to lose that 1 valence electron. So if I look at this picture over here on the right, it doesn't have 3 energy levels anymore. It only has 1, 2. Okay, because that 1 valence electron, it donated it. It like gave its electron away, probably to a non-metal to form a bond. Okay. And so because it gave away that 1 valence electron, the third energy level went away. It doesn't have it anymore because there's no longer an electron in that energy level. And so I can see that it now has a +1 charge. And if I were to rewrite the configuration, that 3s1 has gone away because it lost that valence electron. And so because it lost the electron in that third shell, it has less energy levels. And so that causes it to be smaller. Okay. So when I'm talking about cations or positive ions, I need to know that the positive ions are smaller than their parent atoms. And parent atoms is just the term we use to refer to the neutral atom that it started out as. So it started out as a neutral sodium atom, and then when it lost electrons, it became the sodium ion. And so the parent atom is like what it started out as before it lost the electrons. Okay. And the reason that it is smaller is because positive ions have less energy levels than their parent atoms because they always lose whatever valence electrons they have. And so when they lose the valence electrons, number one, they lose that energy level, but then also it affects that, that nuclear charge, that attraction, because positive ions, they have more protons than electrons. So if I were to compare these two, this sodium atom over here, it has 11 protons and 11 electrons, okay? Because that's what its atomic number is. Over here, it's still sodium, so it still has 11 protons, but it lost a valence electron. So now it only has 10 electrons. So since there are more protons than electrons, that nuclear charge is also going to cause the atom to shrink in because the protons, it's like they're overpowering the electrons. And so there's a stronger attraction for the electrons that are still in the energy levels. Okay. Now, negative ions, they're opposite. Okay. Because they're doing opposite things. So negative ions are anions. These are going to be our nonmetals because nonmetals, they don't lose electrons, they gain electrons. So when we have nonmetals and they gain electrons to become a negative ion or an anion, they actually are going to get bigger. So negative ions are bigger than their parent atoms. And the reason for this, again, it goes back to that attraction, that nuclear charge. Because if I compare these two, they have given me a chlorine atom and a chloride ion. And so if I look at the electron configuration down here, chlorine has 7 valence electrons here in the third energy level. So it's got 7. Oops, no, go back. Sorry, guys. Okay, so it's got 7 valence electrons. And so since it has 7 valence electrons, it wants to gain 1 more to get to that full octet of 8. And so that's what happens. It'll find some nonmetal like sodium, and it will take an electron from that metal like sodium. And so if I look over here now, it has 8 valence electrons in the outer shell because it gained 1 electron. So that's why it has a -1 charge. If I look at the electron configuration, it now ends in 3p6. So that shows me that it has 8 valence electrons. So now, even I did not add an energy level. That electron it still got added to the 3rd energy level. But if I were to compare their numbers now, like we did on the other one, this one I have 17 protons and 17 electrons, the neutral atom, because they're the same. Over here, I still have 17 protons, but now I have 18 electrons. So in this situation, there are less protons, there's more electrons. And so the nuclear charge isn't as strong because there are more electrons. And so the protons aren't attracting them as strongly, okay? And that's basically kind of what this last thing here says. It says that negative ions have more electrons than protons. And so the attraction is decreased, or it's less, okay? So again, all of this relates back to that whole nuclear charge concept of, with positive ions, there are less electrons, there's more protons. And so that causes it to have a higher nuclear charge, and it shrinks in and becomes smaller when it's a positive ion. But for nonmetals, when they gain electrons, there's less protons than there are electrons. And so that causes it to actually expand out because the protons are not attracting all of the electrons as much as they were when it was a neutral atom, okay? So after this, on the next page, there are some practice questions that you guys are gonna do. So make sure, guys, when you're reading these, be very careful on some of these open-ended questions, because like this one, there are 2 parts. You have to state and explain the trend, okay? So state means you're just telling me atomic radius, and then you either say increases down a group or decreases down a group, whichever one it is. That's the state part. You're just telling me, what is it doing? Is it increasing or decreasing? Going down a group or going across a period. The explain is you're telling me why. Okay, so that's where you need to think about the things like the shielding and the nuclear charge and all that stuff, and the protons versus the electrons and the energy levels, etc. Okay, so make sure that when you're doing those types of questions that you address both of those terms, state and explain, because they all say that on like 1 through 4. And then the last couple questions, have you practiced ordering some in order of increasing atomic radius and then increasing ionic radius, okay? I will tell you on ionic radius, because these can be confusing, what you have to look at the effective nuclear charge. Compare the protons that the atom has to the electrons, okay? Because, for example, you have something that's like a +2, a +1, and you're like, well, they're both positive, so how do I know which one is bigger or smaller? Well, compare their effective nuclear charge. So look up on the periodic table, look up their atomic number, and then subtract how many shielding electrons they would have. And the nuclear charges will tell you kind of what order to put them in usually. All right. So that is it for today. I'm going to stop sharing so that we can